Hello and welcome back. This is the circuit we're working on at the end of the last video. We've got our count register, which is actually just the lower 8 bits of an addressing register. We've got this other test register that we're using as some bus interfacing logic. And at the very end of the last video we were looking at the problem where we've got two devices here for driving signals onto our bus. We've just got two devices at the moment, but we have to ensure that only one of the devices is active on the bus at any one point in time. And we solved that problem here just by having the enable input for this chip pass through a NOT inverter from the enable input on this chip. So I can switch this and either get the output from the dip switches or the output from the counter. And what we want to do now is take a look at some other ways of solving that problem that are going to work for more than just two registers. So I'm going to disconnect all of this. And we're going to start a fresh new board. Okay, so the process we are looking at is called demultiplexing. Now what you have is a situation where we have a number of registers on that 16-bit bus, and we would like to be able to select just one of them to assert onto that bus at any given point in time. So if we think about this from a purely logical standpoint, we've got 8 select lines, all active low, and we actually only want one of each of those to be low at any given point in time. So very simply, we've got 8 options. So rather than have 8 lines coming out from whatever circuit is controlling that selection, what it would be far better to do would be to have 3 lines coming out, because that means we've got 3 bits of data which has 8 permutations, and we have 8 things we want to happen. So there's never any question of the 2 things happening at the same time which are incompatible. So anyway, this is what I'd like to look at today. This is the 74LS138 Decoder demultiplexer. So let's have a look at the data sheet. Okay, so this is described as a 3 to 8 line decoder, and numerically that sounds like exactly what we want. We've got the usual timing stuff here. This particular version of it has a propagation delay of 21 nanoseconds, so we can assume that when we've selected the output 21 nanoseconds later, we'll have got the expected output on the line. Let's have a look at the pinout. Okay, so this is fairly common. We've got the ground and the VCC in opposite corners, as we've come to expect. We have 8 output lines. This one's slightly trickier than the last chip we looked at, in that we've got the first 7 lines here in nice numerical order, but then the 8th line, Y7, is over on the other side, but that's pretty easy to deal with. We've got these 3 select lines at the bottom on pins 1, 2 and 3. That's what we're going to use to specify the address of the register that we want on the bus. And we've got 3 enable lines. So have a look at the circuit here. So the enables here, we've got two of the line, well, we got all three lines eventually going into an AND gate through inverted inputs, and so these two are going to be active low, and this one has an extra inverter in front of it, so this is going to be active high input. So we've got a few extra lines to fix there, but apart from that, this looks like it's going to do what we want. Let's get our normal power lines in. Look at those enable lines. Okay, so G1 is on pin 6 here, and that's the one we think is active high. So let's bring that high. And then pins next to it, 4 and 5, are the active low enable lines. So let's bring them low. So then on pins 1, 2 and 3 we have our address lines, our selection. So let's get some wires into those. And for now, let's bring them low. So what are we expecting here? We are expecting that the first output will be selected. Once again, I use one of these sealed resistor arrays. And I will probably do one of those little fast forwards for fitting these LEDs. And last but not least, okay, so I've got the 8 LEDs hooked up to the 8 outputs, and everything is working as we expect. Now, all of these LEDs are on, and this one is off, because we're selecting address 0, which is going to be this, this line here, and these outputs are active low, which is of course exactly what we want on those select lines for the bus driving chips. So I should be able to move these lines. So that is obviously the least significant bit. Moving that means we have selected the second one. That is the second bit, and then this one here should change when I activate this line. Brilliant. Okay, so that's fairly interesting. We've got exactly what we want here. That's job done. We should look at doing something a little bit more with it though. Okay, so we've got these 3 address bits, and it would be nice to see them doing something a little bit more interesting. So I think a good way of doing that would be to stick the output from a counter into those lines. So let's grab this one. I haven't seen this board for a small amount of time. Connect the input here to a clock. So that's out, that's counting nicely now. So okay, I'm just going to look for some slightly longer wires to make this easier. There we go. Okay, why's that gone off? Oh, of course. I need to make up some more of these wires. Okay, so that's the first bit. Second bit, of course, the disconnected bit is floating high, which is why we see the action up at this end. And there's the third bit. So it's quite easy to imagine here how we would have, so these three white wires, instead of being connected into a counting register, would actually go into one of the control units in our processor, and that would output 3 bits of data, and then the register we want can be selected onto the bus. Okay, this is a little bit non-obvious to look at, so whilst these lines are active low, I'm going to swap these LEDs over, drive them off the 5-volt rail and move these wires up here, so then the LEDs will come on when they're selected and it will be a little bit clearer. Okay, so now the LEDs are coming on when the lines are selected, so that's a little bit easier to look at. Okay, so that's the initial problem solved, but this is really quite elegant and quite simple. This is quite a simple and actually fairly cheap chip, so drop one of these in, we can now select any one of 8 registers from 3 lines. So simple, in fact, I think it would actually be pretty nice to make more use of these. So obviously, on those registers we're also going to have a load line. Now this is interesting because whilst we can only tell one register to output to the bus, we could theoretically tell multiple registers to read from the bus. Now this could be pretty handy if, let's say we wanted to reset lots of registers to 0. We could load a 0 into one register, push that onto the bus and tell all the others to load it. But we do have the reset lines on the count register for doing that. There's potentially situations where we might want to put the same value into multiple registers, but in my experience that happens fairly infrequently. So all we'd actually end up doing there is having lots of instruction encodings that we weren't getting very much use out of, and I do think we're going to feel tight on instruction coding space, so we need to be careful about that. So just having one instruction loaded, or sorry, one register loaded at a time would also be quite handy. So we do have this side problem where we've only got 8 combinations here. So if we wired the 8 lines to the load pins on the registers and then use them directly, we would find ourselves in a situation where there was always one register loading, and we might not want that. So there's a few things we can do there. Now, one option would be to get one of these enable lines and also wire that into the control unit, and that would work. So instead of using 3 lines, we're using 4, but we're still saving on the 8 registers. Another possibility is if we were to say not have 8 registers on the bus, we had 7, we could simply have one of these lines not wired to a register. So there would be a safe value, maybe 000 or 111. So one of the LEDs at the end in this that wasn't going to be used for loading. So we've got a variety of different ways of doing it. If we don't have 8 registers, that's probably the easiest way of doing it, because that means we still just have 3 lines and we can drive up to 7 registers. But there's actually additional uses for these select and enable lines. So I'd like to start looking at a couple of those. Now, one thing we should pay attention to is how we'd like the actual lines to operate in the case of an assert to bus or a load from the bus. So if we go back and draw a clock signal, so each one of these divisions is a cycle, and if we were, say, copying between 2 registers, then we've got other stuff going on here. We've got this bus cycle here. So on this point here, we're going to tell one of the registers to assert its value onto the bus. So the first of these will select the appropriate value, and the value will appear on the bus. But more importantly, it's going to appear on the bus at some point over here. So there's going to be a little chunk of time where this is resolving its output, and then there'll be a little chunk of time when the register is resolving its output. But to be honest, that can happen over this entire space if it needs to, because here on the falling edge of the clock is where we would like to tell a register to load. So we got this time for the value to be asserted to the bus, and then this period of time for it to get pulled back in. So that's good, but that means that if we were to simply select the load line using this, then we would be attempting to load from the very beginning. And some of the chips we're using for registers are edge triggered, so they're actually so it's just gonna immediately load whatever value happened to be lying around on the bus, because this isn't quite here yet, and that's not going to work. So if we stay pretending that these lines are active high, what we want to happen is we've got our load command here, and here's the load line into the chip. What we actually want is an AND gate, and we want to AND that with the inverse output from the clock over here. So then what we'll see on this load line is this signal. So that's good. Now, obviously these signals are actually inverted, but we won't worry about that for now. But this does mean that in this version of the circuit we would end up with 8 output lines and 8 AND gates. Now, that's not actually the end of the world. If we had to do that, that would be fine, because we know that we actually get a fair number of the simple gates on a 74 series chip. So we'd only need a couple of the AND chips. But there's actually a much easier way of doing this. Find a longer wire. Okay, so this is our select line, which makes everything stop. So what we can actually do is take this line and attach that to the clock, and what we've got here is the equivalent of ANDing all the outputs with the clock pulse. So we've actually saved ourselves quite a lot of logic here. So okay, the next question would have to be, what do we do if we want more than 8 control lines? Well, that's actually got quite a fairly simple answer. I used orange for these. Right, now these enable lines are actually designed for, well, whatever we need them to do. But we could do a process known as cascading. So if we've got one of these chips, so we've got our 8 output lines and we've got our 3 input control lines, so we could increase the number of outputs we have dramatically by having an additional 3 control lines, one of these chips here, and then 8 of these chips out here, with the outputs from here going into the enable lines of each of these. So then we would find ourselves with 8 times 8, which is 64 of these control lines, and 6 input lines. Now, we're not going to have anything like that many registers, but there are, in addition to 3 to 8 line demultiplexers, you also get 2 to 4 line demultiplexers, so that would give us 32 control lines. But the situations in which I've been looking at in the processor design, I actually max out at needing 16 control lines from one of these demultiplexers. So once again, what we could do is grab a spare inverter up here and invert the control inputs, but we've actually got quite an interesting situation down here where 2 of these enable inputs are active low and 1 of them is active high. So if you're thinking about this as I am, we can do something quite interesting and chain 2 of these together without needing any additional chips. So I'm going to drop the wiring for another one in. Okay, so I have wired up a exact duplicate of this. I've stuck the chip on the left hand side rather than the right, so we can keep the LEDs in a nice neat row here. But as you can see, it's currently mirroring the exact actions of the first one. I've wired the 3 address lines straight across here, and everything is working as we'd expect. So okay, so what I'm going to do here, just to demonstrate this particular property, so I'm going to grab the 4th bit from our counter over here, and there is no 4th select input onto these chips, but what I can do is replace this active high enable signal with this new selection bit. So what you can see here is through half the cycle this one is no longer active. So you can probably follow exactly what I'm going to do here. I can then daisy chain that on to one of the active low inputs on this second chip, and now what we get is our selection is seamlessly extended up to 16 lines without the need of any additional ICs. So that's really cool. I'm actually pretty happy with this, and I can see quite a lot of uses for this configuration in the CPU design. I think I'm basically done for this video. I'm with the little fast forward chunks here. I've no idea how long this one's going to be, but hopefully I've not gone on too long. In the next video I'm going to take a look back at the address registers for the last time. We're going to look at those on the breadboard and basically just check a few things, confirm a few bits of behavior, and then I'll look into transferring them to a circuit, and we can move on to some other portions of the CPU circuit. Thank you. Goodbye.